Okay, here's problem number 1. And we can move this compass needle around. And using this, we can identify the poles. Also notice that you can move the magnet itself. If you grab this, we can move it into the center. And so you can see that the green is the south pole, and the yellow is the north pole, and the compass traces out these dipole field lines that go around the magnet. So if I put the compass needle there, it points in that direction. If I put it down here, it points in the same direction, and that's because the magnetic field of a dipole, you should know what it looks like. It forms these loops around the outside of the dipole. So with the compass and the questions I ask, you should be able to answer the questions for number 1. Second problem gives us 4 wires with carrying current. If we use the little compass needle to see the field around each wire, you can see that the field around each wire is counterclockwise. All 4 of them, the field is counterclockwise. And so if you use right-hand rule number 2, curl your fingers counterclockwise, your thumb points out of the screen. It means the current in all 4 wires is coming out of the screen. So when we go to the configurations, we don't have the compass needle, but we can tap on the screen and it will show us field lines. So if we tap around each wire, it will show us the direction of the current. And when you do that, you can decide, when you see, like this one, you can see on the top is going counterclockwise, so that's good. But the one on the side, the 2 on the side are going clockwise. And you can have fun if you want to just trace out the field. You can just click and it gives you those field lines. Then you go to configuration 2 and you test it again in configuration 3, and that should take care of problem number 2. Okay, simulation number 3, or problem number 3, shows a field which is all pointing in the negative x direction. And we have 5 different animations, so I'm going to pick animation 1 and I'm going to play it. And you see that the charge goes through the field without bending. And animation 2, the charge does the same thing, but has a slightly different motion. So think about that. There's something different between 1 and 2 in how fast the particle moves, so you need to look at that. If we go to animation 3, we see the particle bounces back. Animation 4, it bends one way. And animation 5, it bends the other way. So the question is, what should the particle do? Well, if you know your right-hand rule and you understand F equals QV cross B, you should be able to predict that when a charge moves parallel or anti-parallel to the field, that there'll be no force on it. How is that? Well, the direction of the velocity vector here is in the I hat or x direction. The direction of field is in the negative I hat direction. That's the angle between the 2 vectors is 180 degrees. And so the sine of 180 is 0 and the force is 0. Okay, let's go on to the next one. All right, this one's pretty easy. I don't need to spend much time on it, but there's a configuration 1 and 2 with the field off. So if I press field off and play it, you see the charges, negative charges, move through that way. If I press field on and play it, the negative charges do that. So obviously there's a force on them that force them up to the top of the wire. If I go to configuration 2 and go field off and play it, you see there's positive charges moving the opposite way. Fill the wire, there's no field. If I stop that, put the field on, and then play it, you see the charges do the same thing. They go to the top. So this is a question of what's the direction of the magnetic field that would make the charges do that. You have to answer those questions. That's, once again, right-hand rule number 1. This number 5 is also fairly easy. Once again, you have a compass. Whoops. And we can move it around, and by moving around you can identify the poles, you can see the shape of the field. And so with the compass needle you can identify the poles and see the direction of the field. Then when we go to animation 1, it gives us a wire in the field with a current. What does it say? The current's coming out of the computer screen, so it's coming at us, and so you use right-hand rule number 1 for ILB sine theta, that equation, and you pick, you see all the animations give you a different direction of the force on the wire, and only one of them is correct. And so you need to answer the questions on that. That one's fairly easy too. Okay, the last 5 are a little bit harder. So we have 3 regions of magnetic field, and we take an electron. It tells us an electron, so it's a negative charge, and when we shoot it, it goes into region 1. Region 1 causes it to bend down. Region 2, you can tell, doesn't change its direction. Region 3 bends it up. Region 4 continues to bend it. And watch what happens. So it repeats the behavior in the reverse direction as it comes back. And so what you need to know about this is that a charge in a magnetic field moves in a circle. So make sure you understand all that. And the circle depends on, let me pause the video for a second. Okay, I don't want to lose this screen, so let me just say a few things and go on to the others, and then once I finish I can come back. So there's a lot of the next problems have this situation where a particle enters a magnetic field where the direction of motion is perpendicular to the field, and that causes the particle to move in a circle. So what you can see here is that in region 2 and region 3 and region 4, the circle has the same curvature. So that means the strength of the field and the direction of the field is the same in both these regions. Whereas when it comes into region 1, it bends that way. It bends down. You see, this is bending up, so the field is different. And so you use right-hand rule number 1. When it goes in, if it bends down, point your finger along the x-axis, put your index along the x-axis, your middle finger goes into the screen and your thumb points up. Okay, you got to reverse it. Remember, it's an electron, so if your thumb points up, that's right. So it means the field in region 1 is into the screen, which means the field in region 2 and 3 is out of the screen. You need to practice that. If you're not following it, work it through with your right hand. And what you'll notice is this is a straight line. So there's no bending, there's no force on the electron here, and that means that the field in this region is 0. But because the curvature here is the same and bigger than the curvature here, it means that the field in these regions is stronger than that region. Okay, there's more to say about this, but I want to get on to the other exercises just so you have some idea of what to do. Okay, I'm back without the figure. So take a look at this equation. And this will explain, whoops. So the force on a charge moving through a magnetic field is QV cross B, or QVB sine theta. So when the charge enters the field, it's subject to this force, and its motion will be governed by Newton's second law, the mass times the acceleration. Oops, that's an error. That should be acceleration. Let me stop. Okay, the final solution. So from the simulation, you should have figured that the magnetic force was up, because when you increase the force, this would decrease. They have to equal mg. So if this gets bigger, this is going to get smaller. And so using Newton's second law, F equals ma, we have Fb plus F up minus mg down equals ma equals 0, because they're in equilibrium. And so mg equals the sum of the two. M is going to be the sum of the two divided by g. And F you read off the scale. This you calculate from ILB. Oops, we forgot to mention L. You got to go back to the simulation and measure the length of the wire and divide by g, and that will give you the mass of the particle. I hope you were able to do this on yourself. Good luck.